Hello everyone. Today we'll be exploring a critical area of cloud security and how to protect your application's data from potentially untrusted cloud provider. For this, we'll be using a research paper authored by Andrew Bauman, Marcus Pianado, and Galen Hunt. The paper is titled Untrusted Cloud with Haven. My name is Rohan Chavan and let's start with this presentation, shall we? This is a presentation based a paper which was presented in the UNISEC Symposium on Operating System Design and Implementation in 2014. These are the contents of my presentation. Let's start with the fundamental challenge. When you move your application to cloud, you're inherently placing a significant amount of trust in your cloud provider. This trust extends far beyond just physical infrastructure. As the paper highlights, the trusted computing base (TCB) is a set of components you must trust for security. Your trust should be enormous. It includes not only providers' hardware but also vast amount of complex software like hypervisor, operating systems, management tools, and critically staffed people who have access to this infrastructure. As for a fun fact, did you know that 90% of cloud users unknowingly expose their data potential breach? So, what is the problem at hand? Current cloud computing requires users to trust the provider's software, hardware, and administrators. As we know, Snowden leaks demonstrate the risk of implicit trust in law enforcement bodies' jurisdictions over cloud data replication. This is where the concept of Haven, shielded execution system, comes into play. What is shielded execution? It represents a paradigm shift in how we approach cloud security. Instead of trusting the cloud provider, shielded execution aims to protect your application from the cloud provider. This paper defines this by protecting confidentiality, integrity of your code and data from underlying platforms, clouds operators, OS, and VM and firmware. Think of it like renting a space in co-location facility. You bring your own server, lock it into a cage. Facility simply provides power, cooling, network connectivity. Provider can't see what's inside your cage. Similarly, shielded execution. Cloud provider is reduced to providing raw resources, processor cycles, storage, networking. They can still deny service. They cannot observe or modify your data or code. Haven is a groundbreaking system that leverages Intel's software card extension, achieves shielded execution, a method that protects application from malicious hosts while maintaining performance compatibility with legacy software. Haven is just not a concept, it's a practical solution that redefines how we think about security in the cloud. In this presentation, we'll explore the challenges of running application securely in untrusted environments, how Haven uses SGX and a library operating system to shield these applications, and also the results of testing Haven with real-world applications like an SQL server. So let's start with the term shielded execution. What is it? A shielded execution guarantees confidentiality, that the data is hidden, and integrity, direct execution of the data even when the OS and hypervisor is compromised. Only the inputs you provide and output it generates are visible. The cloud provider cannot tamper with the application's behavior. It will execute correctly and produce the same result as if we are running on a trusted reference hardware. Haven achieves key innovation that has been proposed by the authors in form of Haven is its ability to run unmodified legacy Windows application. This is critical because it avoids the need to rewrite existing code, which can be a huge undertaking. Haven achieves this by leveraging Intel Software Card extensions or SGX. SGX provides a hardware-based security mechanism that allows creating protected regions of memory called enclaves where your application can run securely. This gives the user an end-to-end guarantee of application security to trusting the cloud provider, its software, and any hardware beyond the processor itself. Intel XGX is the fundamental building block that enables Haven. It allows a process to create enclaves, which is isolated regions of memory within the processor's address space, as shown in the figure, which each isolated region. Crucial thing is that code and the data residing inside the enclaves are protected from an outside world. SGX uses dedicated memory region called enclave page caching as as represented here. When data written from enclave to the dynamic RAM, it's automatically encrypted and integrity is protected as shown in the figure here. This prevents cloud provider from snooping or tampering with the data. However, it is important to know that EPC enclave page cache is a limited resource, which introduces challenges that Haven needs to address. So, what are the key features of Intel XGX? It helps in encryption and integrity checks using enclave memory. Attestation. Remote attestation allows enclave to prove the integrity to third party, establishing trust over untrusted networks. And also the isolation provided by Intel SGX. Enclaves are isolated from OS hypervisor and other processes even with the physical access to memory. Moving on, while SGX provides powerful foundation shielding unmodified legacy application presents significant challenge. First, the legacy applications are inherently complex. They weren't designed within the constraints of an enclave. They often rely heavily on the operating system services. They use exception handling, dynamic solutions. A dynamic allocated memory may use a wide range of x86 infrastructure. Secondly, legacy applications are typically written assuming that operating system is trustworthy. However, in an untrusted cloud environment, the host OS could be malicious and attempt to subvert even is derived from drawbridge. An early research project focused on OS compatibilization. The libOS implements Windows API that legacy applications expect, providing the necessary operating system services. But it does so within the protected environment of enclave. The libOS uses a small set of primitives such as thread, virtual memory, or file output. By running the OS inside the enclave, the haven mitigates Lago attacks as the host OS is no longer trusted to provide correct system call results. This is a critical element in achieving the C shielded execution. Shield module implements a strict validation policy for host provided data, rejects invalid or unexpected results from system calls. It hardens the system call interface using cryptographic hashing for. Let's take a look at Haven architecture. Why does it need an architecture as legacy applications would already use it? But the challenges that it faced was legacy applications are complex and depend on a full OS. The host OS cannot be trusted for high ego attacks. The GX has limits small enclave memory. Before we dive into Haven's architecture, let's quickly recap the challenges it faces. We are trying to run complex, unmodified Windows application in a secure enclave. But these applications expect a fully operating system environment. Furthermore, the cloud providers OS can't be trusted, opening the door to IGO attacks. So here are a few components of the enclave that is present between the SGX provided by Intel. Even addresses this challenge carefully by a design layer architecture. At the bottom, we have untrusted host operating system, a standard Windows installation provided by cloud provider. Top of that, we have SGX enclave, protected region of memory enforced by CPU's hardware security features. Inside enclave lies Haven's core, the libOS. The libOS provides necessary Windows APIs and supports that application expects, but it runs entirely with secure enclave. Finally, the top we have unmodified Windows application itself right here. So what is the role of libOS? libOS is like emulating Windows inside the enclave. The heart of Haven's architecture is libOS. It's based on Drawbridge, a research operating system developed by Microsoft Research that was designed for strong compliance, compartmentalization, and security. libOS implements a careful selected subset of Windows API, focusing on essential services that legacy applications commonly use for input and output, memory management, networking. The libOS does not contain functionality related to the application to ensure a minimal trusted computing base. One of the key components of the architecture of Haven are private scheduling, virtual memory, and shield module and untrusted runtime. One of the biggest challenges in Haven's design is dealing with limited size of SGX enclave page cache. Legacy applications can be large and more memory than that's available inside the enclave. Where does that Haven implements a secure paging mechanism that is tamper proof that is tamper proof even by the host OS. The paper does acknowledge performance overhead paging and mention that minimizing paging frequency is an important optimization goal. Moving on, Haven's architecture provides a significant security benefit. It offers strong protection against malicious host OS, enabling running unmodified legacy applications and reduces a trusted computing base. However, it's important to acknowledge that the limitations. The architecture does introduce a performance overhead due to a system called validation and paging. It is also vulnerable to side channel attacks, which are not addressed by Haven. Finally, the security of Haven ultimately relies on security of underlying Intel SGX hardware. Conclude, the architecture of Haven as a libOS is the key to the Haven security and functionality. Mutual distrust is essential in mitigating IO attacks. Secure memory management is critical for handling EPC limits. The threat model used by the authors in this paper is as follows. The key design principle of Haven is mutual distrust. The library OS does not blindly trust the host operating system. Instead, it meticulously validates the result of all system calls. For example, when an application requests memory, the libOS verifies that allocated memory is indeed available and hasn't been tampered by the host OS. Similarly, it checks the integrity of data it read from the files. This distrustful approach ensures that a malicious host OS cannot subvert the protected application by providing incorrect or manipulated system call results. Haven incorporates several key security mechanisms to achieve that robust shielded execution. It uses private scheduling, virtual memory management, as well as encryption at its core level. So, what are the key assumptions used by Haven to perform such an act? The process executes instruction correctly and securely manages enclave memory. The randomness of source cryptographic operations are secure and reliable. These are some of the foundational assumptions that Haven uses for the testing of its proposed system using Intel SGX. The crucial aspect of shielded execution is ensuring that application is indeed running securely inside the enclave and hasn't been compromised. This is achieved through remote attestation. Haven uses a remote attestation mechanism to allow remote party to verify the integrity of shielded program running in the cloud. This provides assurance that the application is running in a secure enclave and hasn't been tampered with without having to trust the cloud provider. What are the excluded threats that Haven and the researchers have excluded in this testing for Haven system? Side channel attacks. Timing and power analysis cache-based attacks are outside Haven scope but remain a potential risk. Physical CPU attacks, direct attacks on the processor package itself, are not addressed by SGX or Haven. Here are some of the evaluation results presented by researchers after conducting a thorough research of Haven on SQL servers and Apache web-based server. The researchers evaluated Haven's performance using real-world and unmodified server applications, namely SQL Server and Apache. It is important to note that the performance measures were done by SGX emulator due to SGX hardware not being available at that time. We found out that the Haven's performance was reasonable, with overhead deemed acceptable for the security benefits it provided. I'm sure it did. 15% performance overhead compared to a native execution for SQL servers, and Apache web servers had a 5% overhead of static web pages. Not that bad. While there is a performance cost associated with shielded execution, security advantages often outweigh the performance impacts, especially in the scenario that we are currently focusing on, where data confidentiality and integrity are paramount. Proposed SGX modification through the evaluation of the Haven model. In developing Haven, the researchers pushed SGX to its limit, identified several limitations in original SGX design. They proposed fixes to address this limitation, and Intel incorporated these fixes into a revised version of SGX specification. This demonstrates the impact of Haven on the evolution of hardware security. What were the challenges that we can recall from the original XA? It was static enclave size. SGX initially required enclave sizes to be fixed at creation, limiting support for large applications. High context switch overhead. Enclave entry exit incurred significant performance costs. N-case cycles per switch and a lack of demand paging. SGX lacked support for paging, requiring all enclave memory to remain in physical RAM. So, what were the proposed SGX modifications by the authors? Dynamic memory allocation allows enclaves to add remove pages at runtime with cooperative host enclave and mechanisms. Faster context switching reduces latency by optimizing hardware instruction for enclave transition. Demand paging support which enabled transmit paging of enclave memory to untrusted storage, ensuring data confidentiality and integrity. What were the impacts of this modification, you may ask? It addressed scalability issues for large memory-intensive applications like SQL Server. It was also incorporated into subsequent SGX revisions, improving usability and performance. Future improvements that the current SGX enclaves have has at its core. Its size is limited to 128 MB and it also restricts large applications. No protection against side channel attacks. Optimization for example handling, reduce enclave transition costs, improve handling of page faults and illegal instruction. Demand loading mechanisms such as reduce memory footprint by loading code on demand. Also, providing an encrypted networking support, a secure communication between enclaves and enable which would enable a VPN-like encrypted tunnel within the cloud. It is important to consider who Haven is trying to protect against as. Haven assumes a powerful adversary that controls most of providers' hardware and all its software. At hardware level, it assumes that the processor itself is implemented correctly and not compromised. The adversary has full control beyond the physical package of the processor, including memory and the I/O devices. At software level, the adversary also controls the cloud provider's entire software stack, including the host OS, hypervisor, management software, platform firmware, BIOS, code executing in system management mode, and device firmware. We do not consider any side channel attacks. It's important to isolate execution It's important to distinguish isolated execution from shielded execution. Isolated execution generally refers to a mechanism that protects the confidentiality and integrity of specific code and data from other actors. Shielded execution builds on an isolation mechanism to provide higher level security properties, guaranteeing confidentiality, integrity of a program. Moreover, in Haven, there is a need for attestation mechanism to establish confidence integrity of a remote shield program. The mechanism provisions secret directly to it, allowing it to operate on encrypted inputs, extend confidentiality beyond the confines of the shielded mechanism. Conclusion. So, what do we find from this paper? So, here are the key takeaways. It demonstrates Haven represents demonstrates a significant step towards building a more secure cloud ecosystem by enabling shielded execution by unmodified legacy applications. It reduces trusted and computing base empowers users with great control over data. This approach helps bridge the gap to fully homomorphic encryption, which is not practical. While Haven is a prototype, it demonstrates feasibility and potential of shielded execution. Future research can explore the further performance optimizations, expanding for support for various applications and operating systems, leveraging emerging hardware security technologies. The cloud platforms provide scalability convenience but requires trust in the providers of software and hardware staff. Even eliminates this trust by requirement by implementing shielded execution, ensuring confidentiality and integrity. Thank you for your attention. This is me, Rohan Chavan, and I would like to thank Dr. Matthew Hicks for providing this opportunity to present this research paper. Thank you.